everybody. Give it a minute for people to join. We do have a couple topics on the agenda today. Don't see the presenters here yet. So we can go ahead and collect some opens if anybody has them while we wait for quorum.
Hi, Jim. This is Jag from Oracle. Just FYI.
Oh, okay, you are here.
Yeah.
Okay. Yeah, sorry about that. Okay, let's just go ahead and get started. Like I said, if you have any opens, you can add them to the agenda now, or Jag, if you're ready, go ahead and present your topic.
Oh, thank you.
Yes, so can everyone see my screen?
Yeah, I can see it.
Okay, great. So I will believe it's time to get started. Okay, so good local time. My name is Yanqing Wen from Oracle, and also known as Tom. And today I want to present our evidence collector called RASTI, which is a short of the remote attestation procedure daemon. I will have this presentation along with my colleague Jack Raymond. Okay, so before we get started, and here are some legal stuff, and we will basically cover the motivation why we want to do RASTI, and also how we solve the problem with RASTI, what what RASTI tries to do, also what type of evidence RASTI is going to collect, and with many type of evidence, if there's any way to minimize the number. For example, we can have the unified interface for both MD7 SMP and the Intel TDX. So we found one using the config TSN. And of course, I will also cover the evidence format and the current development status of RASTI. And before we end in this presentation, I will have my colleague Jack to talk about the challenge of implementing RASTI and we will also have a demo at the end. Okay, so for the motivation part, I would invite my colleague Jack Rahman, who implemented the verification server part, to talk about why we want to do REST. So go ahead, Jack.
Hey, thanks, Tom. I'm Jag Raman. I'm a principal software developer at Oracle. So today I want to introduce RADSD to you and explain our motivation for developing RADSD. So as we all know, hardware root of trust is essential for remote attestation. And in modern systems, there are often multiple attesters from different manufacturers that act as the hardware root of trust. For example, a GPU can have its own ROT. CPU can have a attester, for example, SEV-SMP in AMD. And also the chipset or the motherboard can have a separate BTPM chip that can act as a hardware root of trust. So in this case, the challenge is to collect evidence from all these attesters to provide a comprehensive view of the TCB for the purposes of remote attestation. Additionally, the evidence generated by RADSD should be in a format that is supported by the RADS architecture, so we can integrate with other tools that conform to the data formats specified in the RADS architecture. We couldn't find any tools that were doing it, so we decided to go ahead and implement RADSD. On this topic, I want to mention the multi-verifier topic that's come up in IETF recently, where it discusses composite attestation. Composite evidence. So evidence from multiple attesters. And RADSD is a tool which can facilitate this and is one of the implementations or an example implementation of how we would do attestation with composite evidence. So my coworker Tom will go over the architecture, some of the implementation details, and the current status of this project. And I will circle back at the end of the presentation to discuss the challenges. I want to take some time to thank Thomas Fossetti, who led us in this project and who was also instrumental in guiding and in the architecture of this project. So at the end, we're excited to hear any feedback you have so that it can work for more people, not just us. And I'd be glad to facilitate that. So with that, over to you, Tom.
Okay, so thanks, Jack. So before
excuse me, Tom.
I found there's a raised hand.
Yeah.
Yep.
So there's a raised hand, and we could do like two different ways. If you want to interrupt, that's totally fine. Or if you want to save your thoughts at the end for questions, that's fine too. So whatever works for you. So Osama, please, your question.
Yeah, I'm fine to take it or put it at the end if you like. I just wanted a clarification on what you call as the hardware root of trust. If you want, I can put it now. If you want, we can discuss at the end.
I think for the single question, we can take it for now.
Okay, so basically so my question hopefully will be single. So what I'm thinking about is, does a scenario that I will explain count to you as a single attester or a multiple attester? The scenario is that there is a platform attester and there is a workload attester. So do you consider it as one attester or do you consider it as multiple attester? Particularly, I'm thinking about ARM CCA architecture.
I can take this question. So I think so. It is actually, I would say it is actually nested. So there is a platform or a node attester, and there is a workload attester, which depends on the platform. And the platform itself could be made of multiple attesters. So I would say RADS-D fits as an evidence collector for the node or the platform. And then in one of the future, I think enhancement we are thinking about is similar to what SPIFFE does. Open up a port so a workload can inquire about the TCB of the system or platform. Does that answer your question, Osama?
Not sure. So my understanding of ARM CCA is that it's not the platform, or I think you are using node synonymously. So it's actually the workload attester, which is actually fetching the evidence from platform. So the lead attester in this case is the workload platform, workload attester, and not the platform attester. So what I understood from you is you are thinking the other way around. Is it correct? You are thinking of the platform as the lead attester. To me, it's the opposite. It's the workload attester, which is the lead attester, and it gets or fetches the platform evidence and then presents both to the verifier.
I agree with you. So workload could be the lead attester, but as far as when you want to inquire about the platform, there has to be a single endpoint for it. So there could be a lead attester for the entire workload, and then there could be a separate lead attester for the platform. So the workload now talks to platform to get its TCB or evidence about the TCB, and then it builds it into the evidence that it is constructing about the entire TCB.
Okay, right. Thank you. We can discuss that then. Thanks.
Hey, Thomas.
Hey, Jack, just a clarification. So to Usama's question, RADS-D is the lead attester, right? Is the lead attester that exposes the API and then collects all the sub attesters evidence into one single package that then it signs and sends it over.
It is the lead attester for the platform. Osama was asking about a workload. So workload which runs on a platform, I believe that is a little different. But RADS-D is the lead attester for the platform.
For the system, yes.
Oh,
I think I'm using platform in a different way than you're using it, but it doesn't matter. I'll shut up.
Okay. Yeah, I mean, there is this still question about who is the lead attester when it comes to a scenario where there is both platform and workload. And that's something that we haven't really thought about yet. So maybe we can, that's definitely something that we can talk about at the end of the presentation.
RADS-D is trusted or not?
I'm sorry?
RADS-D is trusted or not?
That comes to one of our questions. RADS-D is trusted.
Okay,
but
thanks.
So we have to, we want to anchor its trust in a hardware rot, but that's something that we are working on. It's not there yet. So we will explain that in the challenges section.
Thanks. Yeah.
Thank you.
Okay, so I believe now we can move on to the current design of RADS-D. And before I talk about that, I want to give you an idea of where the REST is in the overall architecture. So this slide shows our system design for our remote attestation solutions. And here we have three parties. One is the relying party, which use the result from the verifier to perform an action. This, for example, this one can be the relying party can be a key broker service. And of course, on the right-hand side, it shows we have the REST, which generate the evidence for the relying party to send it over to the verifier, which is the remote attestation service for the attestation result. In our scenario, we would expect the relying party to provide the nonce, and REST would returns back an attestation token, which is EAT, the short for anti-attestation token defined by IETF. This token would also include the nonce so that it demonstrates this piece of evidence belongs to the request from the particular relying party, and then the RAM party can send it over to the verifier and get back something called the EAR, the entity attestation result. Okay, so this presentation focus on the REST, and before I go over it, I want to take the question from Mohammed.
Yes, please, if you go back to the previous slide.
Yes.
Okay, so I'm trying to make sense of this from ARM CCA perspective. So as I understand, the attesters block basically will contain the platform attester and a realm attester from ARM CCA perspective, and that's RATS-D. So who will generate the evidence for RATS-D? Because that's a part of the TE itself, right?
Okay, so I believe if I understand your question correctly, you're asking about how we present the evidence for REST itself.
Kind of. First, I'm trying to understand where RATS-D is running. Is it running within the virtual machine? Is it running within the realm?
Yeah,
From the
so
perspective of
yeah,
from the
so
perspective of ARM
mm,
CCA, so it's a part of the realm that I am trying to attest, right? So is this correct?
yeah, so currently we are running REST within the instance, within the VM.
Okay.
Yeah.
Okay. So that would now mean that, and it would be per VM, that would be per realm. So each realm will have one instance of RATS-D, correct?
Yes,
Or will
exactly.
it- Okay, okay, thank you.
Okay, so let's go back to what REST does. So basically now it provides the sum total of the evidence from each leave attester of the platform. So here the leave attesters refers to things like CPU, GPUs, but not the leaf node of a cluster. And for REST, we implement those leaf attester as plugins. These plugins are dynamically loaded when REST starts. REST as the lead attester of the platform, it provides a unified API for anyone to retrieve an attestation token through the RESTful API. And in order to make sure the plugin is not compromised, REST also supports plugin verification. And for now, we consider REST itself as a trusted component, and we can feed the expected SHA-256 checksum for each leaf attesters. Whenever REST is started, it will validate the checksum for each of the leaf attesters. If there's a failure, then REST would report an error. And for some components such as the CPU, I as far as I know, no, MD has something called the VMPLs, and in ARM there are also different exception levels. So that means REST would also need to support for various types of the parking specific options. And now REST is capable of doing this. Also, the remaining party may pick what kind of the evidence should goes into the REST's response. Yeah, we will talk about this in the later slides. So for the leaf attesters for the platform, we would have the list of followings. The first attester I want to mention is the TSM report attesters. The TSM is the short for Trusted Secure Module. It should work for both AMD Ceph SMP and Intel TDX CPU. So through the TSM, we should able to get the attestation report from the secure processor. So, and in the case of Ceph SMP, we may also fetch its X509 certificates. And besides the TSM report, we also want to implement the leaf attesters for the TPMs and GPUs and IMA. So as of today, we only get the TSN reports leaf attester available with REST. And here I want to briefly talk about the TSN itself. So the reason why we use TSN and for the attestation report. Okay, sorry, I saw the question from Mohammed. So please go ahead.
Yeah, sorry, I'm asking too many questions. If you want, I can ask at the end. The last slide was interesting for me. So this is, so I'm trying to get a picture of this in my head. So TSM is basically talking about, again, taking the example of ARM CCA. I am trying to figure out where each of these entity is lying. So TSM to me would mean we are talking about the realm. TPM, I am not sure. That's one of my question. GPU, I believe, is connected to the realm attester. So my first question is, where is the TPM? Is it off the platform or is it within the realm itself?
It is of the platform.
It's off the platform. So it's a real hardware TPM that is per platform. It's not
exactly.
a virtual TPM. Okay. Okay, sounds good. And the GPU and the TPU, so where do they lie? Are they, so how do you kind of visualize that in the RATSD sense? Is it connected to, do you visualize it at the workload level? So is it like at the realm? So when you are fetching the RATSD, when it is running within the realm, so it's fetching the evidence there, or is it in addition to the platform, it's connecting to the GPU to fetch the evidence? How is it kind of being visualized?
Okay, so first of all, I want to mention we haven't implemented the solution for GPU. But regarding your question, I would believe it still needs the support from the physical GPU. So we would believe it is the physical GPU responsibility to provide an attestation report as part of the evidence. And I see there's another reason from David.
Yeah, just to chime in with regard to GPU and NPU and TPU attestation, all that is handled through for confidential compute through a standard called TDISP, which is supported by SPDM for its attestation. So in the Linux kernel community, we're still working as to what the interface for that looks like. There's been one initial proposal that used sysfs for it, but the problem is then you lose the ability to kind of have your signed composite measurements. So there's another version of it floating around currently that uses the netlink interface. So you could essentially grab those measurements via netlink. Now, TDISP basically says that you're pulling the whole device into the trust boundary. It's not on a per workload basis. It's kind of at the security boundary of the TVM at that point. So if you had a workload that had a GPU as part of it, you would want to collect that GPU as part of the evidence for your workload. But the second you bring that GPU into the trust boundary, it's for everything in the trust boundary. It's not just for an individual workload.
So David, if I may ask, so are you saying that you are visualizing it, the connections that you mentioned? So you are thinking of it as being. So you mentioned that you are fetching the evidence, but I'm trying to understand who is actually doing that. Is it the workload, like workload as in sense of the realm? Or from TDX perspective, the VM, the confidential VM or the trust domain. So is it the trust domain who is fetching those, or is it the lower part, like the quoting enclave, or let's say one of the lower parts underneath, or the TDX module maybe? Who is actually doing that, fetching that evidence from the GPU is kind of my question, or who is building that TDISP and all these connections?
So that's a really long explanation. If you want, I can explain it to you later, so we're not
No,
taking up
no.
presentation time. But it happens
Maybe
twice effectively. It's both. The short answer is it's
it's
both.
both.
You need
Okay, okay.
you need the TVM to accept the GPU into its trust boundary to begin with, and then after that, workloads need an interface to be able to request the attestation reports for everything inside the trust boundary, so it could hand it off to a verifier and decide if it wants to release data or models or whatever confidential portions of the workload exist.
Okay, right. Thanks.
Okay, yeah. So thanks, David, for the insight of implementing the GPU or TPU attestation. Yeah, we may discuss this after the presentation.
Yeah, sorry, one more thing. I would talk with Dan Williams. He runs a kernel SIG on Thursday evenings Pacific time. And they're discussing a lot of this stuff currently for TDX Connect and SEV TIO. So that work is ongoing. If you want to be involved in what the interfaces look like so that you have input for the RADS-D here, that would be a good place to talk with them about it.
I see. Yeah, thanks, David, for your recommendation. Okay, so yes, so as you can see in this slide, yeah, of course, vendors have proprietary attestation report formats, and of course, just like what David has mentioned, there's always an effort to unify the way to retrieve the evidence, so that users may uh, may obtain the evidence without knowing the proprietary part. Yeah, so actually we use AMD Safe SMP for example, and it is actually the first confidential computing solution that introduced the character device, which make it possible for the VM to retrieve an attestation report for iOcto. And to retrieve the attestation report, we use something called the config fs. is a file-based system-based manager of kernel objects, and it has been adopted as a cross-vendor mechanism to retrieve Cocoa attestation report starting kernel 6.7. And the usage is also shown in this slide. Basically, you would create a path for the attestation report. You would after you make the directory for such report, put under the config fstsn, it would create several objects under the directory. So the one which we used to write the nonce to is called the ing blob. And after we write the data to the ing blob, we would get the attestation report from the aux blob. Yeah, we will talk about it in the next slide. Okay, so the TSN report consists of several objects. One is called the outblob. This is the most important one. This is the one we use to get the SSN report. And of course, because both MDSMV and TDX is using the same interface, we would also need to know which is the provider. In the case of SFSMP, the provider would be the SCV gas, and for TDX it would be TDS gas. It's a read-only object, and TSN report also allows the vendors to specify auxiliary data in another object called auxbob. And here for the SFSMP, they put the certificate table. The certificate would include several keys from the MD root keys, which signs the MD signing keys and form and certificate chain. The chain ends at the key which signs the attestation report. So basically, we can validate the signature and try to validate the whole certificate chain from the MD's root key. And for each object here, they are all in base64 format. For the TSM report particularly, it would expect a 64 by nonce. So it's actually a base 64 representation of the 64 by data. And that is also what REST they would expect when the user make the HTTP request to get the evidence. And I will talk about this in the next slide. Okay, so here we will also want to bring up what the evidence format would look like. So we actually wrap the evidence from each of the leaf attester as a CNW collection. So this is the issue which would require multi-verifiers to deal with the verification. And as of today, because we only have the SafeSMP, so the evidence generated by REST would looks like the right-hand side. We make it as an EAT, and within the EAT there's a CNW collections, which consists of the single CNW for the SafeSMP. And here we actually use the TSN, so there's no worry about well, if we have REST running on the TDX on the Intel CPU. And for the media part, we have already registered it with IANA, and thanks Thomas for registering the media type for us. Okay, so Mohammed, please go ahead.
Yeah, so I'm thinking from a tested TLS perspective, where would the attested TLS connection terminate in this diagram? So I actually have some objection to this diagram. It's not showing the exact picture, but let's say, so you have a VM and RATSD is running within the VM. And my question is that particularly would RATSD play a role in terminating the connection, or would it be to the other logic that I have, let's say, let's call that the user logic versus the RATSD logic that you will develop?
Okay. So sorry, Mohammed, have you done all for questions, or I can answer your question now?
Yeah, sure, please.
Okay. So yeah, so now we implement each of the leaf attesters as processes. So actually, there's no internet connection between the REST itself and the leaf attesters. Yeah, but regarding the workload attestation, which we would have several attesters, and in that case, that means there are several VMs, each with the components from REST. And in that case, we do expect to use attested TLS to establish the connection between them. But for now, because we are focusing on the single VM attestation, so we don't have to worry about the connection between the processes running within the same VM. So
No, actually, just to clarify, so my question was not within that. So I'm thinking more about, let's say I am a relying party, right? So I want to check that the VM is in a good state and so on. So who will I connect to in this figure? So will I connect to RATSD? So where will the connection terminate in the attester? So that's independent of how many blocks you have or how many parties you are connecting to. Eventually, as a relying party, I need some guarantees that I am connecting to a genuine platform, right? So that has this measurement and so on. So where would that TLS connection terminate in this case?
I think I can
Would
take
it
a
be
shot.
RATS? Sure.
So I believe it will be RADST because so right now, just for clarification, the picture you're looking at is the whole VM. And the connection would terminate inside RADST because we don't trust anyone else. And then we establish trust in RADST based on some hardware root of trust. Since the communication between the RADST module and leaf attesters or not via network, the TLS connection will terminate in RADST if we choose to do it. It currently does not support attested TLS though.
Okay, so that makes perfect sense to me that the TLS connects here, but I'm a bit confused if you say that the whole block is the VM, which means that previously you said it's a hardware TPM. If the TPM is within the VM, I would assume that's a virtual TPM. So that's the only thing which is a bit unclear to me now.
So,
I think
okay, yeah.
I think it is showing the T is the whole TCB, Usama, if I understand correctly. It's the TCB where different testers are
Right.
different. Yeah. So
Sure.
don't get
That
kind of
was that was also my understanding, but Jag confused me a little bit by saying that the picture is of the whole. So Yogesh, are you also viewing it like that? This whole is the part below is the platform and the part above is the kind of some part of the VM, right? Is this also your understanding?
Yes, I mean, effectively,
Okay.
this is the whole trusted computing base where the attestation can happen. The pink or whatever color I see, orange, that is the entire trusted computing base which can be attested. So that's how you should look at it.
Okay, sure. So yeah, okay. I think I understand now. Thanks.
I'm sorry for confusing you, Usama.
No problem. It's so for the tested TLS team, we have every week these kind of conversations. Where is the TLS terminating? Where is the TPM? Where is this and that? So it's I can totally understand that. So that's perfectly fine. Thanks a lot.
Okay, so yes, so thanks Jack for the further explanation of this. And so now REST only handles the simple connections, so there's no attached TLS. So to use REST, one would just need to do a post request to REST. And here we use the port number 8895, and the endpoint is called REST chars, which stands for the change response. And here we would expect the user to specify the nonce in the request body in the basic C4 format. And what will be written by REST is an EAT token. So here you will see there's a JSON which has the EAT nonce, which is the same as the provided nonce in the request body. And also we will see the CNW. The value of CNW is the attest sorry, it's the TSN report I mentioned earlier. So this is a serialization of the struct. The struct would have the out blob, aux blob, and the service provider, as I mentioned in the previous slides. So I'm not going to decode the basic C4 string right now, but we have that decoded in the next slide. So this is a decoded CNW collection. As you can see, it has the CNW tag as well as the evidence from the TSN attester. And here is the current upstream status of REST. So here I would need to appreciate the reviews from Thomas Fasatis. Yeah, he provided many advice on how we implement our first prototype. So now REST would have the main lead attester for the TCB itself, and also the config TSN div attester. And now REST would able to take the query options and also allows the user to specify what goes into the evidence, and also the cryptographically verified leaf attesters. And for other development effort we haven't done yet are more types of leaf attesters, and also we should also sign the CNW collections in the next release. Okay, so Mohammed, please go ahead.
Yeah, so in the previous slides, you were showing the CMW collection and all that. And in the TDX, there is one field which is user data. I think you named it in some of the slides. What is it for AMD. I forgot, but anyway, so I'm trying to make sense of, is it for TDX it's 64 bytes? And is it the same for AMD, or how does that work across platform, because you're supporting both? Like the user provided data, optional auxiliary data is, I think, what you call it. That's the user provided data, right?
No, this is not provided by the user. Actually, if you look at the actually if you look at the config FSTSN spec, you will see Oxprop is actually a read-only object. What is writable for the user is called the ing blob. And regarding the 64 byte nonce, it's the same for MD7SMP.
Okay, so what do you call that? So where do I see that? So what's the name of that? Which one? The 64 bytes that the user provides.
Okay,
What?
it's not shown here. So
Okay.
okay, yeah, it's not shown here. But I can speak of the TDX attestation report, but for the SMP, you would get the same 64 byte nonce in its attestation report available through Outblob.
Right.
And that's
So
for
basically,
ARM. The same goes for ARM. Yeah.
okay, so it's 64 bytes for all the architectures. That's why you have the same length. Okay, perfect. Thanks.
Yes, that's true. Okay, so probably we are running out of time, but before we talk about the change, I want to do a short demo of how we use REST. Let me share a different screen.
Can I ask a quick question while we're getting ready? So since TPM attestation becomes part of your overall flow, one concern is, I don't know about UFI TPMs, but apparently TPMs can be slow and single-threaded. Yeah, maybe not slow if it's UFI, but certainly single-threaded. So if you're going to put this on a data center server and attest multiple virtual machines at once, and each of them wants to talk to the TPM, we should probably engineer some sort of a caching mechanism that's still secure. And this goes for all composite attestations of the sort. It's not just a problem here, it's just a general issue.
Sorry, can you repeat your last sentence?
So you will want to make sure that this scales for data centers, and if your TPMs are single-threaded, so the UFI, physical TPM, and you put this on a data center server that has multiple VMs, potentially hundreds of VMs that want to do attestation, you may find yourself putting in a bottleneck.
Yeah, I see.
And, I mean, one way of dealing with caching is, physical TPMs are not going to have different measurements. But you need to figure out how to deal with freshness. But this is a generic problem for anything involving TPMs.
Yeah, I was about to say that's true, but it doesn't apply to the REDSD layer, right? Like if you run REDSD, like the ship has already sailed to scale out the TPM. So I guess not sure what you can do at the REDSD level about this, right?
Caching without the TPM measurements might be one way, but it just needs to be thought of, because if you design deploy something and then in the data center it doesn't scale, that's a serious problem.
But it's more of a, I mean, it's RATSD is kind of supporting it, supporting TPM as a root of trust. If the designer doesn't want it, it can just not use it. So I don't understand
I think
how
the question is about
can't wait.
caching, which is a fair option. I think when there are multiple agents asking for the same piece of information, then potentially a caching strategy can work out. It just needs to
You can't
bind.
say You can't say don't use it because it can be used
Yeah.
for something like geolocation, for data sovereignty. So I know where my VM is running based on what the device TPM says. So this is not an optional consideration.
But caching is just a non-reuse, right?
I don't want to propose a solution here. It's just something I want to think about.
Yeah, okay,
Yeah.
okay, sure. Yeah.
Yeah.
Yeah, I
I'm
agree it's a
sorry.
challenge. Yeah, I agree with it.
I'm sorry, like I'm kind of missing this caching issue with TPM and how
This
it's
argument is
how
just
it
that the
looks.
throughput of a TPM might not allow the large scale attestations that you might want to have if you deploy REDS-D on like all TVMs for all workloads. And if every workload now wants to kind of also test the TPM, then you quickly run into like bottlenecks of the TPM because it's just not, as a single threaded TPM, not fast enough to support that big requirement, right? Like that much throughput.
Got it.
So that was a comment.
Okay, thanks for explaining, Frizz. I appreciate that. One thing I wanted to add here is the TPM that's used with the attesters is a VTPM, right? So that actually uses the CPU cycles. It does not use the physical TPM located on the chipset. Is that correct? So the
But
TPM is an
previously,
emulated TPM.
so Jack, previously you said when I was asking, it was you or the other presenter. So one of you said that it's a physical TPM. Now I'm very confused. You are now saying it's a virtual TPM?
So within the attester, it is always the virtual TPM, right? Is it possible to provide a physical TPM within an attester? I'm not sure.
Yes.
Like a TE. Oh, okay.
Yes, you can. I can. I was like working around this this last week, and using QEMU, for example, you can pass through the TPM hardware, but this has also limitations, such as you can only pass the TPM physical module to only one VM at a time on a single machine. Meanwhile, the VTPM provides several sockets that are passed by like the kernel. So basically, it's more of a file system that you are passing to each VM. And I think what Azure is currently doing with the VTPM one, each VM is assigned also socket, but this is being provided by the paravisor as a solution, like with running in a separate TD. And there's, I think from Intel, there's this VTPM TD implementation where this software solution is running within a VTPM. Within a TD. So basically, this is an extra layer of security.
So for Microsoft, it's not the separate TD, or let's say not a separate VM. So for Microsoft, my understanding is that each VM has a VTPM inside. So it's not a separate VM, so to say.
Yes. So each VM gets a VTPM socket, and this VTPM socket will be through the paravisor is channeling to like an entity that is running the VTPM implementation, because it's a pure software. The VTPM is just pure software solution, not backed by hardware, to my knowledge. But please, someone correct me if I'm talking wrong.
Sure. So my confusion was actually from the previous slides when one of the presenters actually said that the TPM on that figure was physical TPM. So what I'm hearing now, RATS-D doesn't support physical TPM, and the TPM shown there was a virtual TPM. Jag, is this correct?
That is correct. First of all, sorry for the confusion.
Sorry for
But the overall point is it really does not matter, right? Whether if it's a physical TPM or a virtual TPM. RATS-D assumes the VTPM, or as far as RATS-D is concerned, the TPM is trusted. And the trust model for the VTPM is beyond the scope of this. I saw some presentation from, I believe, Mike Stunes and Greg Costel about how they implemented VTPM in Microsoft. So if you're able to get a VTPM that is in theory having a good trust model, then I think that should extend to any solutions that use RADS-D.
Sure.
I think fully agree with Jag. Fully agree with Jag. I don't understand like whether it is VTPM or TPM. The architecture presented here with RADS-D should be fully supportive of both the kind of models. So I don't see it as a bottleneck here.
Sure. I mean, it's not a bottleneck. So I think Mark was concerned about the performance bottleneck for physical TPM being single threaded versus a virtual TPM, which you can have multiple threads. So, yeah, I think that was a performance bottleneck kind of perspective. So, but you have virtual TPM. But one concern here is you mentioned Mike's talk, and there basically you need to trust the cloud provider for that. So they have that virtual TPM within the VMs, confidential VMs. That's fine. Each VM has its own TPM, but the virtual TPM. But the problem there is that their Azure is the root of trust for all of that. So you have to trust Azure in that case.
The VTPM EK is signed by the TEE, so it is rooted to the hardware. You can get that extra the extra signature in the chain.
Sure, you can have that binding which Mike presented, but the root of trust, if you remember his right side of the figure, so that was all that chain is the whole chain of trust for VTPM was coming from Microsoft. So you put in that in the R data for the trusted execution environment. Let's say for TTX, you put in that R data, that public key of that VTPM. But that VTPM chain itself is all routing from from Microsoft.
You can get, for example, for TDs, you can get a TD quote for the VTPM's EK.
I'm not sure how. So that's running within the same VM.
It's a VTPM index that you can get a manifest. Inside that manifest is a TD quote.
So you're saying that you could have. So how could you have like it's a part of the same VM that you are trying to attest? How could you have the
paravisor is part of the VM. It is in the TD.
Right.
So that, yeah.
But you, but
I think paravisor is part of the VM, but it's running at a different privilege level. That's what's kind of missing, I think, when you compare it to the when you compare it to CCA. So it's running at highest privilege level. Yeah.
Yeah, for time's sake, we could probably take this offline for different discussion on VTPMs. But yeah, I think we're down to like 1 minute, so I don't know if Tom or Jag, you want to do quickly the.
Yeah, actually, can we continue the discussion next time? Because I feel like we kind of got stuck at different like components and didn't really discuss benefits of the framework itself. And I think that also has like merit, right? Things like what is it useful for, like how to collect. Is it necessary if we all have EAT, right? These level discussions I would also be interested in next time. And now we kind of got stuck at these. I got lots of thumbs up. Thanks, guys. Okay, yeah.
Yeah, let's continue. Yep.
Okay.
Put that on the topic list for next meeting.
Okay. Yeah. Yes. Thanks for bringing this up. Okay. So I still.
Yeah, I would appreciate if we could discuss it next meeting. Yeah, so that we can. There's a lot of feedback here, so I want to. I don't want to lose it. I want to be able to make it to a constructive solution. Thanks.
Yeah, thanks. Okay, so let's do a very quick demo. So basically, we just make a post request to REST through the REST trust endpoint, and we will get the output, and it has been written to a file called out Okay, so this is how it looks like. So yes, so there are so many messages in the CNW. I will talk about that later. But as you can see the response is a JSON which has the EAT profile called GitHub 2024 Verizon REST, along with the EAT nonce, which is the same as what is specified in the request body. And for this one, these are this is a very long line. It's the basis for serialization of a CNW collection. Okay, so because we are running out of time, I will hand the presentation over to Jack for the challenges for REST.
Do we have any time, or
No,
should
I
we
think we're
just?
out.
Yeah.
Let's continue
so-
this, and for next week, I think there's still going to be some more feedback, and I think that's good stopping point. Talk about the challenges
Yeah.
and
Thanks.
Great, thank you.
Thank you.
yeah, thanks a lot, guys.
Thanks.
It's really great.
Thank you.
Very
you so
interesting.
much.
Thanks.
Thanks, folks. Bye bye. See you next time.
Thank you. Bye bye.